Hey everybody, I hope that everybody's finding this system to be a little bit helpful. So we're going to pick up right where we left off. We were talking about reaction rates, and actually the previous lesson that we looked at dealt with the initial rates method. So we were looking at determining a rate law equation that would satisfy us determining the rate of a chemical reaction no matter which concentrations of reactants were given. The last part of this particular chapter deals with something called reaction mechanisms and the catalysts for this reaction. So a rate mechanism is a series of steps that makes up the overall reaction. Each particular step in this grouping of steps, this rate mechanism, is called an elementary reaction, and they involve single molecular events, so a single bond breaking, something along those lines, just a single molecular event. So let's take a look at the first equation there under example number 1. As you guys can see here, we have two NOs plus an O2 producing two NO2s. When we have that, and we actually look at how this thing actually plays out, it actually plays out into two individual steps. So the first of the two elementary reactions is NO react with an O2 to produce an NO3. And then that NO3 is subsequently consumed in the second reaction. As you can see right here, I'll circle that for you guys right here. Uh, when it reacts with the second NO to produce the two NO2s. When we look at the two elementary steps, these single molecular events, they sum together to produce the overall reaction. So when elementary reactions are added together, as shown above, as I mentioned, you always get the overall reaction. Any molecules that are formed in the elementary reactions are called reaction intermediates, and they are subsequently consumed in following reactions. Um, One of the things that we talked about in class when we looked at rates of reaction was dealt with molecularity. And so when we're talking about molecularity, we're talking about the number of reacting particles. So we know that unimolecular reactions are reactions that deal with a single molecule. Bimolecular, which are by far the most common, deal with two reacting particles or two reacting molecules. And intermolecular would be exceedingly rare. I think we had a conversation in class regarding, walking down a hall, bumping into a person. That's fairly common, but bumping into two different people at the exact same time is much more complicated and much rarer of an event. And those would be termomolecular reactions. Now, of course, they do exist, but they are rare. Um, and so we have to look at, most of the time, it's going to be a bimolecular reaction. The nice part about these ones is, instead of having to determine the exponents of the rate laws, they are actually determined by the coefficients. So if you recall the previous lesson, which dealt with the initial rates method, we had to calculate the exponents. In this particular case, when we're dealing with elementary reactions, because they are single molecular events, we're just looking at the coefficient in front of the chemicals in the reaction to determine what the exponents are. So for example, if we had reaction A, or reactant I should say A, producing products, then the rate law for that particular elementary reaction would be K, which is, remember, is our rate constant. The magnitude of that tells us how quickly it goes, times the concentration of A to the power of 1. Now it's to the power of 1 because the coefficient that's in front of A is 1. In the second example here, we have A plus B, so we have two reacting particles here, A and B. Both of them have coefficients of 1, as you guys can see here, and then as a result, our rate law for that is K times the concentration of A to the power of 1 times the concentration of B to the power of 1, as you guys can see. And then, of course, in the third example here, we have 2A, so two of the same reacting particle, but because we have that 2 there, the rate law exponent for that particular elementary step is equivalent to the 2 that we have here. And then the last example is kind of self-explanatory, right? So you have 2A and a B, which means your exponents for your rate law are to the power of 2 and to the power of 1 for A and B respectively. So when we are looking at these reactions, we are interested in determining which one of these steps is going to be the slowest step, because the slowest step in a reaction always determines the overall rate. So think about an example from your everyday life that might have a rate determining step. So there's tons of examples that you can have from your everyday life, but here's a good example. So let's say we have a bagel, and I want to produce at the end of this whole process a bagel that is toasted and buttered. So I have a bagel in my initial elementary step, and I'm going to toast my bagel. Notice that it is a single event. I'm just toasting. That we determine to be the slow step in the reaction. Of course, in the next step, we have to take that toasted bagel and then we have to butter it. Now, the buttering of the bagel doesn't take very long. The toasting takes a long time. That's why the toasting is the slow event. But what you'll also notice is that the toasted bagel is present as a product in the first reaction and a reactant in the second reaction. So it's exactly what we were talking about earlier, being a reaction intermediate. It is subsequently consumed in the following reaction. So basically what we get is bagel goes and butter gives us a toasted butter bagel. Now that's a good example because I can start pumping out bagels. Let's say I was on breakfast duty, for example. I can only pump out bagels as fast as they are toasted. So if toasting takes 2 minutes, let's say, and buttering takes 30 seconds, then I always have buttered bagels, but I don't have toasted bagels for very long, right? It takes a long time to toast, and then once it's toasted, it's immediately buttered. And that's what we're talking about with these reaction mechanisms. So what we're really talking about is the idea that one of the steps in these processes is going to be the slow step, and the other one is going to be the fast step. So how can we use this to determine rate laws and whether these reaction mechanisms that we're coming up with are going to be true? So consider the following reaction. We have two NOs plus two H2s goes to one N2 and two H2Os, as you guys can see in this first equation here. And it says the rate law that was determined by experiment was found to be this. So when we go back to the previous lesson, we take some measurements via experiment, then we can determine the rate law. So we found out that the rate law for this particular expression was rate is equal to K times the concentration of NO to the power of 2 times the concentration of H2 to the power of 1. And then a chemist proposes the following reaction. So when we talk about making these propositions, there's a lot of chemistry involved in that, and you guys don't know enough chemistry yet to do this. So we would be providing you with the intermediate equations, and what we're going to be asking you to do is determine whether the reaction mechanism is a reasonable mechanism. So the chemist proposes these two steps. He says that two NOs plus an H2 is going to produce N2O plus H2O in the first step, and they've determined that that'll be the slow step, as you guys can see right here. And then the second step is the N2O plus H2. So notice that the N2O, which you have here and here, those are the reaction intermediates. That N2O is going to then ultimately produce or get consumed in the second reaction with another H2 to produce the N2 and the H2O that you guys see in the overall, and that will be our fast one. So this step, this slow step, is the step we're always waiting on. We can't go any faster than this step can go. So essentially, as soon as this N2O is produced, it's consumed immediately in the next step to go to the final products here. So to determine or to solve these problems, to figure out whether these mechanisms are reasonable or not, what you need to do is you need to satisfy two conditions. The first condition that you have to satisfy is that all of the elementary steps add up to give you the overall reactions. If they don't all add up to give you the overall reaction, then it's not a possible mechanism. So if we follow this and we add them up algebraically, and we take the two, you'll notice that the N2O that you see here and here, they'll cancel out, and any chemicals that are on the same side that are the exact same chemicals, they're added together. So you have an H2 on the left here and an H2 on the left here. They sum together to give us two H2s. Same thing with the H2Os. We've got an H2 on the right and an H2 on the right. They sum to give us two H2Os. And so ultimately what that produces is the overall reaction as was shown up above here. The rate mechanism, according to the experimental data that we found, was here. It was given in this particular case. Now, of course, when we're looking at the rate at which this reaction can go, it's the slow step that's going to determine how quickly this reaction can move forward. And so because these are elementary steps, we can look at the stoichiometry of the rate determining step, or the slow step in the reaction, to then determine what the rate law should be. So if we take a look here, we've satisfied the first condition in that all of the elementary steps, when summed together, produce the overall reaction. And then the second thing we have to do is look at the slow step and produce the rate law based on that slow step, and then match it. Does this match the experimentally determined rate law? And so what we do is we look at the slow step, which is that first step here, and we notice that our coefficient for NO is a 2 and our coefficient for H2 is a 1, and you'll notice that we get a 2 and a 1 here in the rate law as determined by the reaction mechanism. That also matches the experimentally determined rate law that was shown and given in the question. So if you have both of those conditions, one that it sums together to produce the overall reaction, and that the slow steps rate mechanism matches the overall rate mechanism as determined by experiment, if you have those two conditions met, then you have a situation where the reaction mechanism is considered to be reasonable. Now, how does this play into catalysts? So we talked a little bit about catalysts. We mentioned in class that catalysts are chemicals that can be added to a particular system that are not consumed. They don't take part in the chemical reaction. Whatever you put in, you're going to get out, and they make the reaction go faster. Well, how do they do that? What happens is when a catalyst is added to a chemical reaction, we end up in a situation where instead of the activation energy being, let's say, this amount, the activation energy is much, much, much lower. It's this amount. Now, how does that happen? Well, it turns out that the chemicals oftentimes do get consumed, but they get reproduced later on in the chemical reaction. And so if they're produced and then consumed, it's as if they were never used at all because they're still present at the end of it. And so what happens is that when you add this catalyst, it rearranges the intermediate steps. It rearranges those equations. And so you end up in a situation where, by rearranging those equations, perhaps adding an equation, changing a particular reaction, or something along those lines, it's able to produce a reaction that requires less activation energy. And of course, when a reaction requires less activation energy, if you remember our Maxwell-Boltzmann distribution, if we have a reaction where we have the a fraction of collisions that have sufficient energy being this amount, and this is my activation energy. If I lower my activation energy now, if let's say I put it this much, now I have all of this plus the original amount in there in terms of the fraction of collisions that then have sufficient energy to get the reaction to move forward. And so if I have a larger fraction of collisions that have sufficient energy, I'm going to end up with a faster chemical reaction. So that's how catalysts work. They actually go in there and they rearrange the activation energy in order to do that. Now, do all catalysts work like this? Well, biological catalysts are a little bit different. In biological catalysts, we don't have the issue of having sufficient energy. The issue that we have with biological molecules, I should say, when they want to react, is their size. And so if you remember back to when we looked at theories of reaction rates, and we looked at kinetic molecular theory, when we looked at the actual reactants coming together and hitting not only with the correct amount of energy, but also hitting with the right orientation, biological catalysts grab very large molecules and orient them in the right position so that they can actually react. Now, we do have two particular models for this. One of them is the lock and key model, and the second one is the induced fit model. And so what happened is you have some substrates. So let's say we had two compounds. Let's say we had this red one here and this blue one, and they need to react together. But because these are huge molecules, to actually get them to orient themselves in the right place is very difficult. And so here comes a biological catalyst, which we call an enzyme, which will grab a hold of these two particular substrates and then force them to be in the correct position to produce a product, which in this particular case is this purple little blob here. Now, the lock and key model is an easy one to understand in that one lock is activated by one key, or this enzyme, this little slots that you see here and here only fit this substrate and this substrate. So they lock in there, and when they've filled those spots, they're able to react. The second example here is another model that we have. It's called the induced fit model. And then this one's probably more so towards what is actually correct. And so you end up in a situation where you have two substrates. They'll come into this area here, and I failed to mention earlier that that area is also present in the other one. We call that the active site in an enzyme. And so what happens is as these molecules come in, the actual shape of the molecule that makes up the enzyme changes to those particular molecules, and as it changes, it's able to grab hold of those substrates, and as that grabs hold of it, it's able to create the product here, and that's how biological catalysts work. So that was our first lesson. I hope that went well. If you have any questions, please email me, and we'll go from there.